And if the superalloys of the Raptor 3 represent the hardened hardware of the engine, then the cooling channels embedded within them represent its vascular system. In a traditional liquid rocket engine, cooling is often an afterthought of assembly, a series of tubes brazed onto a nozzle or holes drilled through a manifold. But in the Raptor 3, the cooling architecture is so deeply integrated into the structural matrix that the two are indistinguishable. To achieve the power densities required for Starship, SpaceX had to move beyond subtractive manufacturing and embrace a philosophy where geometry is limited only by the resolution of a laser. And the microfluidic labyrinth beyond the drill bit. To appreciate the complexity of the Raptor 3 cooling vanes, one must first understand the limitations of the drill and weld era. In legacy engines, cooling channels were typically straight lines. If you wanted to move liquid methane around a high-heat zone, you drilled a hole. If the path needed to curve, you drilled two holes at an angle and plugged the intersection. This created dead zones in the fluid flow stagnant pockets where the propellant would sit, overheat, and potentially coke, leading to a catastrophic blockage. And the Raptor 3, by contrast, utilizes what can be described as a microfluidic labyrinth. Imagine an ant farm where the tunnels aren't just random paths, but mathematically optimized conduits designed to maximize surface area contact while minimizing pressure drop. These channels do not follow straight lines. They twist, taper, and bifurcate with a biological precision. They are carved into the very walls of the combustion chamber and the nozzle throat, often just millimeters away from the 3,000 degrees Celsius inferno of the main combustion zone. And for the graduate engineer, this is a problem of computational fluid dynamics translated into physical topology. In a high-pressure environment, every degree of a curve matters. A sharp turn creates a pressure spike. A gentle, variable radius curve maintains the momentum budget of the propellant. By using 3D printing, SpaceX can vary the cross-sectional area of a single cooling channel along its entire length. They can make the channel wider where the heat flux is highest and narrower where they need to accelerate the fluid to increase the convective heat transfer coefficient. This level of spatial granularity is impossible with a drill bit, but it is the native language of additive manufacturing. And direct metal laser sintering, printing with fire. The process used to create these structures is direct metal laser sintering, or more broadly, laser powder bed fusion. If the Raptor number 3 is a digital-first engine, direct metal laser sintering is the compiler that turns code into matter. And the process begins with a bed of atomized SX500 or copper alloy powder, where each particle is roughly 20 to 40 microns in diameter, thinner than a human hair. A high-powered fiber laser then traces the slice of the engine, welding the powder into a solid layer. The bed drops by a fraction of a millimeter, a new layer of powder is spread, and the process repeats. This is printing with fire. And from a systems perspective, direct metal laser sintering allows for monolithic integration. In previous iterations of rocket technology, a cooling jacket might consist of an inner liner, an outer jacket, and hundreds of individual cooling tubes brazed between them. Each brazed joint was a single point of failure, a potential leak path that could lead to an engine-rich exhaust event. By printing the channels directly into the structural wall, SpaceX eliminates the interface entirely. The cooling channel isn't on the wall, it is the wall. And for the computer science reader, this is the hardware equivalent of inlining a function. Instead of calling an external library, a separate cooling tube, and dealing with the overhead of the interface, the weld, the logic is woven directly into the main execution flow, the chamber wall. This reduces the attack surface for mechanical failure and increases the overall system throughput by allowing for higher internal pressures without the risk of joint separation. And topology, optimization, and generative design. The design of these channels is not just the work of a human engineer with a CAD program. It is increasingly the result of generative design algorithms. And when designing a cooling circuit for a 350-bar engine, the variables are overwhelming, thermal conductivity, fluid viscosity, structural hoop stress, and mass constraints. SpaceX uses topology optimization software to grow the cooling structures. The engineer defines the boundary conditions, the heat load on the inner wall, and the required structural strength, and the software iterates through thousands of generations of geometry to find the most efficient path. And the resulting structures often look alien or organic. They resemble the internal structure of a bird's bone or the root system of a tree. This is because nature has already solved the problem of high-efficiency transport under structural load. These organic shapes are computationally perfect, but manufacture impossible unless you are using a 3D printer. And in this digital-to-physical pipeline, the Raptor 3 is less of a machine and more of a physical manifestation of an optimization result. The 3D printer does not care if the path is a straight line or a complex fractal. The cost of complexity in additive manufacturing is nearly zero. This allows SpaceX to deploy high-fidelity cooling solutions that would have been laughed out of a machine shop 30 years ago. and the zero-trust manufacturing model. Beyond the geometry, 3D printing enables a fundamental shift in manufacturing simplification. The standard aerospace model involves a massive supply chain. Company A casts the housing, Company B drills the holes, Company C provides the tubes, and Company D performs the final assembly. Each handoff is an opportunity for a data loss or a quality control error. And SpaceX's approach with the Raptor 3 is to consolidate these subroutines into a single execution block. By printing large sections of the engine as single pieces, they eliminate friction of assembly, no more aligning hundreds of tiny parts. Mass penalty, no need for heavy flanges, bolts, or thick weld beads. Inspection latency, instead of X-raying 500 individual welds, they can use in situ monitoring during the print process. And this is kernel-level integration. Just as a modern SoC, or system on a chip, integrates the CPU, GPU, and memory controller onto a single die to reduce latency and power consumption, the Raptor 3 integrates the injector plate, the cooling channels, and the structural jacket into a single printed die. This is why the Raptor 3 looks so much cleaner than the Raptor 1 or 2. The complexity hasn't been removed, it has been encapsulated within the printed walls. In managing the surface roughness paradox, one of the graduate-level challenges of 3D printing cooling channels is internal surface roughness. When you weld metal powder with a laser, the resulting surface isn't perfectly smooth. It has a sintered texture. In a standard pipe, you want a smooth surface to reduce friction. However, in a cooling channel, a certain amount of microturbulence is actually desirable. And this is the boundary layer disruption strategy. In a perfectly smooth tube, a laminar boundary layer of fluid can form against the wall, acting as an unintended insulator. By precisely controlling the print parameters, SpaceX can engineer the internal roughness of the channels to act as turbulators. These microscopic bumps trip the flow, forcing the cool methane to constantly mix and hit the hot wall. And it is a delicate balance. Too much roughness and you lose too much pressure. A head loss in hydraulic terms, too little and the wall melts. SpaceX engineers treat this roughness as a tunable parameter in their code. They can adjust the laser's wobble or hatch pattern to create specific textures that optimize heat transfer for different sections of the engine. And the build-as-test feedback loop, the move to 3D printing, also revolutionized the iteration velocity of the Starship program. In traditional manufacturing, changing a cooling channel's path meant ordering new tooling, such as molds, jigs, and fixtures, which could take months. With DMLS, changing the cooling geometry is as simple as updating the source code. And if a test fire at the McGregor facility reveals a hot spot on the nozzle at T+40 seconds, the engineers don't just patch the hardware, they refactor the CAD model. They might add a bifurcation in the cooling channel at that specific coordinate to increase flow. They upload the new build file to the printers in Hawthorne, and 48 hours later, a V2.1 engine component is being sintered. And this is continuous integration or continuous deployment, known as CI/CD, applied to heavy industry. The engine is never finished. It is simply in a constant state of beta testing and optimization. This is the secret to how SpaceX achieved the 350-bar milestone, while other aerospace entities were still stuck in the design phase of their next-generation engines. They did not just design a better engine. They built a manufacturing compiler that allows them to evolve the engine faster than the laws of physics can find a way to break it. And scaling the labyrinth from prototype to fleet. Finally, we must address the scale of this ambition. It is one thing to 3D print a small component for a laboratory test. It is quite another to print a fleet of engines for a Mars-bound Starship. And each Raptor 3 requires the precise coordination of multiple large-format DMLS machines. SpaceX has built one of the largest additive manufacturing server farms in the world to handle this load. This distributed manufacturing allows them to print multiple engine sections in parallel, which are then fused together using high-precision electron beam welding. And the result is a hardware stack that is both incredibly complex and deceptively simple. By hiding the labyrinth inside the metal, SpaceX has created an engine that is easier to maintain and more reliable in the harsh environment of space. There are no external tubes to get crushed, no exposed sensors to be sheared off by debris, and no complex plumbing to leak. And this leads us to the ultimate goal of all this metallurgical and geometric wizardry. All the SX500 superalloys and all the 3D printed cooling vanes exist for one single, brutal metric, pressure. Without the ability to survive the heat and the chemistry, you can never reach the mechanical limits of the engine's cycle. But with these systems in place, the Raptor 3 can push into a regime of physics that was previously thought to be the red line of material science. And the integration of these cooling vanes into the superalloy matrix is what finally provides the structural confidence to turn the pumps to their absolute limit, leading us directly into the most significant achievement of the Raptor's development, 6.1 chamber pressure, the 350-bar milestone.